Giving out
Okay, everybody, thanks for showing up. I'm very happy to have visiting us in Cambridge. She's going to tell us about new phases of superunions.
Okay, hello. Hello. Well, let me thank Dan for the invitation. It's actually been really amazing being back here. I think after 3.5 years now, tons of changes have happened in the department, so it's really fun to see. Okay, so today I'll tell you about some work that came out last year in July, but actually something that I started working on in 2010 before I started my PhD. So it only about took me 12 years to finish this project. So in this work, we studied static phases of super Yang-Mills, and in an upcoming work, which will hopefully next month, but more likely in April, we'll have the generalization of these phases to rotating phases. And in the rotating case, you have certain new, we claim, new interesting supersymmetric phases as well. Okay, so the idea is relatively simple. We're going to use ADS-CFT. And the ADS-CFT correspondence, at least this version, the oldest version of this correspondence, makes a statement that super Yang-Mills n equal to 4 super Yang-Mills in 4 dimensions, and the dynamics of various low dimension operators in this theory is described equivalently by type 2B superstring theory on ADS5 times S5. And the parameters of the theory are related in a very simple way. So the 't Hooft coupling is inverse of the string scale, and then n squared is related to G string. So I'm only going to study this in a very simple limit. Of course, this is the famous planar limit, where I first take n goes to infinity, which corresponds to taking G string goes to 0. So from the stringy point of view, this is simply restricting yourself to just classical calculations, so just the sphere contributions to the stringy worldsheet. And then I also simultaneously take lambda goes to infinity, which corresponds to throwing away all higher derivative couplings in my effective field theory. So in this limit, when I take both of these limits simultaneously, it turns out that the bulk theory, the dual gravitational theory, reduces to a very simple theory, which is simply classical type 2B supergravity with no alpha prime corrections. And of course, in this limit, because the effective coupling of the theory is lambda, and I'm taking lambda to infinity, so the boundary theory is strongly coupled. The implication of these statements is very simple. If I'm interested in studying equilibrium thermal phases of strongly coupled super Yang-Mills, these phases can be studied by alternatively analyzing stationary, which comes from equilibrium, black hole solutions, and here black hole means that's why they're thermal, solutions of classical type 2B supergravity. So that's what I'll be doing in this talk. Okay. So what we should be doing, of course, is to search for generic stationary solutions which have asymptotically ADS5 times S5 asymptotics in type 2B supergravity, so in 10 dimensions. This is what we should be doing. But for all intents and purposes, even if you try to do this numerically, this is an impossible problem. It's a 9-dimensional problem, and the hardest numerical problems that are being done right now are these supernova explosion simulations, and those are 7-dimensional problems. So this is completely impossible to do. So the first simplification that we can try to do is to do a KK reduction around the S5 modes, integrate out all the massive fields, and then we'll be left over with, and here I'm putting in parentheses, believed to be, because this hasn't really been proved, n equal to 8 gauge supergravity in 5 dimensions. So we've simplified it a little bit, but it's still very complicated because it has tons and tons of fields. So we're going to simplify one more time, or 2 more times. The second simplification is we'll truncate to the SO6, what's known as SO6 gauge supergravity. And this theory contains just a single graviton and the 15 fields which transform in the adjoint of SO6 and 20 scalars. So all the 2-form fields have been thrown out. Okay. In fact, in this theory, people have already constructed a few black hole solutions. So this is doable. But for our purposes, we're going to start with something simpler. But our goal eventually is to maybe go to this sector and study black holes in this sector. But today in the talk, I'm going to tell you about a further simplification of this sector, which is known as U1 cubed gauge supergravity. Here you truncate to the Cartan of this SO6. And so when you truncate to the Cartan, the bosonic sector contains a single graviton, 3 gauge fields corresponding to the U1 cube, so 3 abelian gauge fields, and in total 5 scalars. There's the 2 neutral scalars, which live in the supergravity multiplet, and then you have 3 charged scalars, which are charged under these U1 cubed. Black hole solutions. I'll mention this. No. All the known black hole solutions are the solutions in which these charge scalars are 0. The goal will be to study solutions where the charge scalars are not equal to 0, for reasons that I will explain in the next 2 slides. 1/16, Susie. Though in this sector, there might well be also 1/8 BPS black holes, but those haven't been found yet. But everything I'm going to talk about today is 1/16 BPS. Oh, in this sector, it's n equal to 2. Yeah. That one is also n equals to 2. Yeah. Okay. I'll write down the explicit action for you guys in a couple of slides. But before I do that, let me just clarify exactly what all the symmetries are of this theory and what I'll be using to classify all of my solutions. So the full symmetry group here is this SO1, which gives us the energy of the state. SO4, which is the 2 angular momenta. So the Cartans of SO4 is J1 and J2. So those are the 2 angular momenta. And the Cartans of SO6, which is the R symmetry group from the super Yang-Mills point of view. And well, it's just the isometry group of the S5 on which you're compactifying. And the 3 R charges for that is labeled by Q1, Q2, and Q3. Okay, so the most general solutions that one could in principle study are parameterized by 6 independent parameters. Okay, and of course these satisfy some BPS bound. So if you are interested in supersymmetric solutions, then supersymmetric solutions satisfy a very simple relation where E, the energy, is completely fixed in terms of all the other charges. Okay. So in the talk today, I'll I will only discuss these hairy solutions. And by hairy solutions, I mean the solutions for which charge scalars are not equal to 0. And in particular, I'll focus on these sectors of the theory. So we'll start off by describing static solutions. And for static solutions, the angular momenta are just turned off completely. And I'm going to work in one sector where you have 2 equal charges. So Q1 equal to Q2 and Q3 is 0. We'll also discuss single charge solutions in which Q3 is non-zero. And then towards the end of this talk, I'll tell you a little bit about upcoming work in which we turn on rotation. So the angular momentum is non-trivial, but only with J1 equal to J2. As it turns out, when J1 is not equal to J2, the equations that you have to solve become PDEs, and they're much harder to solve analytically. We haven't yet done any of that. Yes. These good. No, but these you can't have static supersymmetric solutions. Yes. So as I've written over here, these are not supersymmetric. In fact, mostly the motivation for even solving problem number 1 and 2 was to start with a simple case to understand how to do our calculations, because as you'll see, the calculations are a bit tricky to do. And then once we understand exactly how the calculations are done and what technologies are needed to do that, then we can generalize to the rotating case, which is more interesting. And we claim that in these rotating cases, the solutions that we'll construct have a non-trivial SUSY limit, and they will correspond to new SUSY phases that have not been previously studied. We don't. We actually solve equations of motion and then take the BPS limit of that. I'll show you a few plots, but the extremal limit is not supersymmetric. It cuts off. You just have an extremal black hole, but it's not a supersymmetric black hole. Yeah.
bound? Is it saturated or not?
No, they're not. They're not. Exactly. Yes. But not in the rotating case. In the rotating case, we'll show that there does exist a limit in which it's extremal and supersymmetric. But in the static case, that limit doesn't exist.
So the E is still linear in Q, but just not the same coefficients.
Yeah. The extremality bound is just distinct from the T plus one and so. It's some nonlinear form. It's a nonlinear function of these charges. It's not a simple linear function. Okay. I have a plot which we'll see this exactly. Okay. So let me start off by this is the outline for my talk. I'm going to start off by simply telling you about some history stuff and some of the more interesting recent developments that are happening, hopefully to simply situate yourself as to why I think this problem is interesting. Then I'll tell you about this work that came out in July, where we studied static solutions. I'll go into some details about how we constructed these, how the analytic part of these solutions, how they were constructed. And my collaborators, George and Oscar, I should have mentioned this. This work is in collaboration with George Santos and Oscar Diaz, who are numerical GR. They construct the solutions numerically. I construct them analytically, and then we compare. So I'll tell you about the analytic construction of these solutions. Then I'll tell you about some upcoming work where we turn on rotations and then how they have interesting SUSY limits. Well, everything that I'm saying here has an analog in n equal to 4, because every single black hole described over here describes a thermal phase in super Young modes. So the goal is to understand the phase diagram of super Young modes. Fill up the entire phase diagram with studying all the phases, understanding which is dominant and which ensemble. That's kind of it. Okay. So what we have done is focus on hairy solutions, but all previously known solutions, except for one paper that came out in 2010 by Minwala and his group, where they studied hairy solutions. But every other solution and the solutions that I'm going to talk about right now are what's called bald solutions. For these, all the charged scalar fields are just 0. So this is the limit where you go back to minimal supergravity. Okay, so the first thing that is interesting is that, in fact, the most general non-BPS black hole solution is actually known. It was derived by Wu in 2011. So it's a very frustrating paper because he doesn't explain, he just writes down the solution. And the solution is so complicated that even Mathematica can't confirm that it is a solution. But if you plug in explicit numbers and then ask it to numerically check it, then you get 0 every single time within numerical error precision. So we believe it's a solution, but it can't analytically check that it's a solution. It's really complicated. And then the SUSY limit of these black holes was also constructed, and this is the famous Gutowski-Real. Well, they call Gutowski-Real, but there is in fact Kunduri-Luccietti-Real in 2006. But so of course, remember the most general black hole depends on 6 parameters. When I take the SUSY limit, the energy becomes eBPS, which is a function of the charges. So you might have expected that the most general supersymmetric black hole depends on 5 parameters. But in fact, it turns out that the SUSY black holes that were constructed here satisfy this non-trivial charge relation. So these black holes are in fact parameterized by 4 independent numbers. And I'm going to refer to this delta as quote unquote the 5th parameter. And all known black holes have the 5th parameter equal to 0. Well, as I'm going to show, the supersymmetric charge, I'm going to construct for you in the later part of my talk, supersymmetric charged hairy black hole solutions for which delta is non-zero. Yes. In minimal supergravity, you can just directly solve the BPS equations and find the most general solution, which is what these authors did. And the most general solution in minimal supergravity definitely only contains 4 parameters. So you can understand this from a limiting procedure if you want. So what happens is, as you try to take the BPS limit, you end up with a geometry which has closed time-like curves outside of the horizon. It becomes complex. So if you want to have a well-defined geometry, you want to make sure that these closed time-like curves are hidden behind the horizon. So you then have to take a second limit to make it a well-defined geometry, and therefore reduce the number of parameters by 2 instead of 1. So an open puzzle is, do there exist SUSY black holes with delta not equal to 0? It has a much nicer interpretation in the grand canonical ensemble. So in the grand canonical ensemble, if you do a Legendre transform of this entire function, it's simply a sum over the fugacities. So it's a linear function of the fugacities in the grand canonical ensemble, but doing the Legendre transform gives us this nonlinear function. Well, sorry, maybe I should have mentioned all of my Q's and J's are rescaled with respect to n squared. So they're in units of n squared. Yeah. Yeah. I'm only doing the classical solution, so all the charges are already the ones I'm looking at are all n squared anyway. And subleading corrections, which come from one loop determinants, are not going to compute in any case. So I should have mentioned, but my E, Q1, Q2, Q3, J1, J2 are all rescaled by n squared. A priori, I don't see why not. I don't have a proof for that. Yes, the problem is that the most general hairy solutions are not known at all. So there's few solutions. In fact, there are no other solutions apart from the ones that I'm going to show you that are known. In the known examples, delta is roughly proportional to the amplitude of the charge scalar. So yeah, we would like to conjecture that in fact delta is proportional to this charge scalar amplitude. We don't have a proof. We just have like 2 examples, if you consider that enough. Okay. On the other side, there have also been interesting computations from the boundary side of this, which in fact sort of explain this charge relation in a really nice way. And if you compute the Witten index, you can show that the most general index in super Yang-Mills also depends on exactly 4 fugacities. So it depends on exactly delta 1, delta 2, delta 3, and there isn't an independent fugacity omega 1, omega 2 for J1 and J2, but it's just a single omega, and you can check that with these combinations, it's completely supersymmetric. And recent techniques have told us how to compute this index. You complexify one of these fugacities in a certain interesting way, and then you compute these. You get these new saddle points in your matrix integral. And people have been able to show that by computing the index with these complex fugacities, you can in fact, and then doing Legendre transform, you can reproduce precisely the entropy of these Gutowski-Real black holes that were discussed over here. So you might say, well, that's great. We had 4 potentials for the index. We have 4 parameters for the black hole. So this seems to explain why delta has to be 0. Yes, of course. I'm computing an index, so it's all supersymmetric. This is the supersymmetric one. No, these solutions are supersymmetric. These are the ones in minimal supergravity. The Gutowski-Real black hole solutions are supersymmetric. They're also rotating. I haven't gotten to the solutions I've constructed yet. I'm just giving you a history of known solutions. So you might have said, that's great. We don't need really to explore this anymore, except that there was work also in 2018. In fact, the same year that this index paper came out, where by George Santos and Julia, where they numerically constructed a black hole, a supersymmetric black hole, which has 3 equal charges, Q1 equal to Q2 equal to Q3, J1 equal to J2, but no charge relation among these parameters. So it was a 2-parameter supersymmetric black hole solution. So it does not satisfy the charge relation. Delta is not equal to 0. And in fact, in this solution, if you simply compute delta, you find that delta is proportional to the amplitude of the charge scalar. Then you go back to the Gutowski-Real black hole. Yeah. Yes. Yeah, just not a PDE, it's an ODE. And you just set up the problem in a box and you just solve numerically. Yeah, with the appropriate gauge fixing that needs to be done in numerical, as you do in numerical relativity. Yes, same issue. Numerics, you actually can't do the numerical, you can't solve the BPS equations numerically. You also can't solve them analytically in general. So what you always do is to solve the equations of motion and then take a BPS limit. And then you have to, take some limit you have to sort of make sure that the limit is well defined. That is a problem, actually. That is well, not a problem. That is something that has to be completely argued that it's a well-defined limit and that we can actually take it. That's actually where we are currently at in the project. We have the limit and it gives us supersymmetric black holes, but we want to confirm that this limit is in fact well-defined. For that, you need to do a separate and near horizon analysis of the SUSY equations. Okay. So in that solution, which of course that was numerically constructed, you could easily show that delta is charged scalar. So the question is this actually a more general statement than just this one example? We now have two other examples in which this is true. So I'll show you that towards the end of the talk. Yeah. Yeah.
And maybe we will have got that situation or not have the same information, but you're just saying that Laplace transform is done with relative conflict.
Yes, exactly. Okay. There's also another really interesting thing. Yeah. Well, it doesn't contribute to the index clearly because the index automatically has a charge relation. Yeah. The index will always give you delta equal to 0. So these are presumably supersymmetric black holes in which you have those short SUSY representations which combine into long representations, which are supersymmetric, but they don't show up in the index. So it's likely that we will actually not be able to count the microstates of this of such a black hole ever. Okay, but that's for a later problem. The first step is to actually just understand all the phases. Actually, this index calculation, which I just briefly mentioned to you, has another interesting feature, which we are yet to understand. There we find that there's also an order n² number of states in the 1/8 BPS sector, which you obtain by taking this index and you take a delta 3 goes to 0 limit. And in that limit, you end up projecting to a 1/8 BPS sector, and you end up finding, as the authors of this paper showed, it's in this paper, you also end up finding an order n² number of states. So this actually suggests that there's a 1/8 BPS black hole as well, and that has never been found. So another interesting question is, what is the gravity dual? So just to answer your question, which I know you asked me earlier this week, there are 3 qualitatively distinct type of 1/8 BPS sectors. So there's a sector in which Q1 plus Q2 is 0. There's a sector in which J1 plus J2 is 0. And there's a sector in which Q3 plus J2 is 0. The first 2 sectors have been completely understood. You can just write down all the states exactly, and they're never order n². This is the only sector which has not been fully understood because it has a much richer structure. And so there's hints that this has order n² states. We don't know the set of states even in the free limit for this sector. The first 2 things, one of them is in the chiral ring, so you just write down all the states, and the other one, the first 2 ones that I told you, Q1 plus Q2 equal to 0 and J1 plus J2 equal to 0, are completely understood. And we know that there are no order n² states in those 1/8 BPS sectors. This is the only one that had not been previously analyzed. And this index calculation at least seems to suggest that it does have order n² states.
If you just start with the backward one system.
Yeah.
Backward. Try to take this limit, does any cycle go very small Like if you just be naive, very naive and try to take the
You get a zero entropy solution.
something goes.
Okay. So I've told you a lot about the history and stuff. Hopefully I've motivated it enough to understand that there's clearly some more things we can try to learn in this problem. So let me start by explaining what results we have. So I'll start off with the static solutions. So these guys are not supersymmetric. They don't admit a SUSY limit at all. But as I said, this is the motivation for understanding static solutions was to simply set up the problem and understand how calculations are done. As you'll see, they're quite complicated to do. So I'll first off show you the results, and then I'll tell you how we derive them. Okay, so here it is, the explicit action that we're working with. In principle, all you have to do is find equations of motion and solve. Okay, that's the entire problem that I'm trying to solve over here. Okay, so in the let's start with the two equal charge setup, where I have it's a static solution, so J1 equal to J2 equal to 0, and two of the charges are equal. The third charge is set to 0, and this is a generic non-supersymmetric black hole. So my E is arbitrary, and E is greater than 2Q, which is the BPS bound. So you can show that solutions in this sector are obtained by setting A1 equal to A2, phi1 equal to phi2, x1 equal to x2. These are all. So phi's are the charge scalar fields. X's are the neutral scalar fields. And x1, x2, x3 is 1. So there's two neutral scalar fields. Okay. And then it's a one-dimensional problem. Everything is a function of just one parameter r. You just plug into the equations of motion and you can solve it numerically or analytically. I'll tell you how we did it analytically later. Let me just tell you the results. Well, of course, you also need to have boundary conditions, and we simply impose asymptotically globally ADS boundary conditions at infinity. And then if I have a zero entropy solution, then I simply say that everything is finite at the origin. Or if I have a black hole solution, then I have some horizon at some value of r, and then everything is finite on the horizon. Okay, so here are some results. So here's the phase diagram of the solutions that we have. So remember, we have parameterized by E and Q. This is E equal to 2Q, which is the BPS bound. So solutions can only exist in this side of the graph. So the bald black hole that was previously known in this paper by Svechik, Liu, and Pope exists in this region. So the purple line she is the extremality bound. So as you can see, it doesn't go all the way out to the SUSY limit. And it's parameterized by two independent parameters, eta and r, which you can then map back to E and L. And so in the entire green region, these black holes exist. And they have order n squared entropy. Then another interesting solution is just the supersymmetric soliton. So this is a solution with no horizon. So it's order 1 entropy. But it's completely supersymmetric here. So here these functions are always written in this form, and then this is some explicit function which it satisfies some differential equation and doesn't have a closed analytic solution, but you can solve it numerically. So this is a supersymmetric solution. Okay. It's non-singular everywhere. Yeah, completely regular, non-singular. So along the whole line, whole SUSY line. So it's I've mentioned it. It's a one-parameter solution parameterized by this label Q. Yes. Good. Okay, so now the next question to ask is, now we have charge scalar. So these were black holes without any charge scalar. So this is a ball black hole. But if I turn on charge scalars, then you can have superradiant instability. So the next question to ask is, when are these black holes unstable to these superradiant instabilities? So we can ask this question at a linear level. So we can simply solve for the linear charge scalar solution and look for time-dependent solutions of this type. And whenever the imaginary part of omega becomes positive, then that means you have an exponentially growing solution, which means that you expect to have a superradiant instability. And you can actually show that the black holes becomes unstable along this blue line. So everywhere on top of this blue line, the black holes are actually unstable to charge scalar condensation. And therefore, the expectation should be that if I construct these hairy solutions, they exist precisely above this line. because the original black hole becomes unstable, charge scalar starts to condensate, and then you have a new, hopefully the end point of this condensation process is a new solution in which you have a black hole in equilibrium with a charged condensate. In fact, you can do all of this complicated, you can solve this complicated problem here, but there's actually an extremely nice non-interacting toy model, which you can use to predict the same blue curve to very high degree of accuracy, actually. In fact, for like up to charge 3, it matches exactly, and it only starts deviating somewhere around here. And the linear model is really, really simple. You simply treat the, you consider the hairy black hole as an equilibrium mix and a non-interacting mix of the static SUSY solution that I just showed you and the original CLP black hole. So since everything is non-interacting, the total mass of the system is mass of black hole plus the mass of the soliton, which is supersymmetric, so it's equal to 2q. And then the total charge is simply q plus qs. And then you simply extremize the entropy of the mix, because that's the most dominant solution, will be where the entropy is maximum. And it turns out that's just equal to mu equal to 1. This is simply the statement that the soliton and the black hole are in chemical equilibrium. And so when you solve this equation, you get the radius of the black hole to be a function of m and q, and you get the charge of the soliton to also be a function of m and q. And the hairy black hole exists only when r is positive and qs is positive. So r is positive means that there is a black hole with non-trivial entropy, order n squared entropy, and qs greater than 0 means there is hair. There is non-trivial scalar hair. And these inequalities precisely give you this curve right here, which you can then confirm with explicit calculation in the full nonlinear GR. So this is in fact the full phase space in the 2-charge case. You have the ball black holes here, then along the blue line, they become unstable. The unstable leads to scalar condensation, and then the hairy black holes take over. In the region where they overlap, the hairy black holes have higher entropy, so they're dominant solutions. And then the hairy black holes limit all the way down to the soliton. And therefore, the original area where there was no phase in this original area is now completely covered by these hairy black holes. This is a toy model. I'm saying this blue line can be extremely well predicted by this toy model. So of course, the correct way to predict this blue line is to solve this problem. Oh, as I said, the red region, there's this full inequality, R positive and Q positive. And if you solve these two inequalities and plot them on an MQ plane, then it's this entire red region over here. Yeah, so we have a total charge and total mass, which is distributed in some way across the black hole and the soliton. This is a toy model where we're treating them as non-interacting freedom. As I said, we are allowed to trust it because it reproduces the actual exact answer. The blue line is the exact answer. Well, this we get from the full nonlinear solution. All I'm trying to say is that if you didn't want to go through the trouble of doing the whole nonlinear calculation, this toy model actually gives us a very good approximation to the actual answer. Yes, for small values of charge and mass. So in this region over here, the solutions, the exact solutions actually do look like a non-interacting mix. I'm going to show you in a couple of slides. Yeah. I'm just saying you can use the toy model as to predict what's going to happen. In fact, that's what we do because we solve this in perturbation theory. And in order to understand how to set up the perturbative expansion, we first do the non-interacting model that tells us where to set up the problem, and then we do the full nonlinear calculation. The soliton is linearly stable. Yeah. Okay. So you can also study this in the grand canonical ensemble if you wanted. So here we have thermal ADS. In this pink region, we have both the thermal ADS solution and the bald black hole, the CLP black hole solution, but thermal ADS is dominant. This is the line of Hawking phase transition. And then you have the CLP black hole over here. These blue dots actually show you the line of superradiant instability. But as it turns out, in the grand canonical ensemble, these hairy solutions are always subdominant. And this is a region of a continuous phase transition right here. In the static case, the soliton is the only thing. But we already knew that. You need to turn on rotation to see anything non-trivial. Okay. Okay. So then in the paper, we also analyze the single chart setup, but everything is exactly analogous, but I won't go through the details. You have the same CLP solution, but now you see in this limit, it does have the extremal limit, which is indeed supersymmetric, but it's singular. So it actually limits to a singular soliton and not a regular supersymmetric solution. There is also a regular soliton solution along the red line, which is given by this. And the regular solution happens when C1 is non-zero. C1 is 0. That's the line of superradiant instability. Again, something you can predict if you wanted with the linear model. And then the hairy black holes exist in this region. And in this region, as you take the limit down to the soliton, you go to the singular soliton. You go to the regular soliton again. Okay. Here, there's something interesting that happens in the grand canonical ensemble. Almost everything else is the same, except for this black dot, which looks like to be a 0th order phase transition, which we know doesn't happen in the thermodynamic limit. So this is an indication of the fact that we're clearly missing a phase. So there must be some new phase in the sector that we haven't yet found yet. 1/16. Yeah. In the grand canonical ensemble, the hairy solutions are never dominant. They're always subdominant. So they're not showing up in this phase diagram. The green region is always the bald black hole solutions. But what happens here in that bald black hole limit is that this is thermal ADS, and this is the bald black hole phase, and this black dotted line denotes this 0th order phase transition. The blue dotted, exactly. Yeah. So we know that there's an instability, and we know that hairy solutions exist in this range over here, but they're not dominant. So there must be something new happening to smooth out this phase transition here. There must be a new phase, but we haven't found it yet. No, not for the soliton, I think. Yeah. Yes. Yeah. Yeah. Okay. So now let me just spend a little bit of time explaining how we constructed these solutions analytically, and then after that I'll tell you the supersymmetric cases. Okay. So the way we do it, at least analytically, the way we do it is we construct it using perturbation theory. So let me start with the soliton, not the hairy black hole, but just the soliton, because that's actually the simple case. So we treat the soliton as a perturbation around ADS. So we expand out the charge scalar field and all other functions that we had in our metric in this way. So the base solution F0 is pure ADS. F0 is GTT. So this is just the ADS solution, and epsilon is a formal small parameter that we just expand around.
Black hole solution, that was your
Yes. Yes. I haven't come to the hairy solution yet. I'm just showing you how we do the perturbative expansion for soliton. Then the next step will be hairy black hole. There'll be some more difficulties in the hairy solution that we'll have to deal with. The bald solution. So I'm going to treat the hairy black hole as a perturbative expansion around the bald black hole. Oh, that we don't know. We haven't found anything. We don't know. That's an open question. There must be some phase, but it's at the moment missing. Okay, so then all we do is you plug this in, you plug this type of expansion into the equations of motion and just solve it order by order in epsilon. So this is super easy to do. You can show that at every order in epsilon, you get some very nice, some set of second order and first order differential equations, and they have exact solutions that you can just solve. In fact, it's so easy, you can automate it on Mathematica. I think I've done it up to order epsilon to the 40, just to convince myself that nothing funny is happening, and you get a really nice smooth solution. And remember, I'm solving equations of motion, but once you solve it, you can then check whether that solution is itself supersymmetric. And we find that the solution is indeed supersymmetric. For the two charge case, we don't have an exact metric for, so we had to solve it using perturbation theory. For the one charge case, the exact solution is already known. So for that, we don't need to do a perturbative expansion. Okay, so this is easy, no problem whatsoever. In the hairy black hole is set up in exactly the same way. We do a similar perturbative expansion, except that the base solution now is no longer ADS, but it's the ball black hole solution that we started with. Okay. Of course, the problem now is that because these ball black hole initial solution is so complicated, the differential equations that you get at every order in epsilon is not solvable. So what I'm going to do is then take a second expansion in R. So I'm going to assume R is also small, so I have a second perturbative parameter. And the reason that I'm doing that is very clear, because you can see when R is small, this F naught simply becomes ADS. So in that limit, it essentially goes back to the soliton expansion that I just told you about. And we know how to solve the soliton problem. So I'm actually going to do a double perturbative expansion in epsilon and in R. R is the horizon radius. Okay, sounds good. However, the problem, of course, is that when I said you take R to be small, I was keeping small r finite in that limit. That means that this expansion that I'm doing is only valid when I'm sitting really far away from the black hole. If I'm sitting near the horizon of the black hole, then the radial coordinate is of the same size as capital R. So you see that when you do the perturbative expansion, this perturbative expansion that I do over here is only valid when my radial coordinate is very large compared to square root of R, which you can just see from this expansion right here. So this leading order term is of the same size as the subleading term is of the same size as the leading term when small r is of this size. So clearly this type of perturbative expansion is only going to be valid when R is large. So this is what I'm calling the far field region. To fix this, then I need to do another expansion. So I define a new variable y, which is R divided by square root of R, and then do a small r expansion, keeping y finite. In this way, I'm zooming into the region when the radius is of the order of square root of R. Well, then you can show, in fact, that this solution is also valid in a very particular region. So when R is much less than 1, but still much greater than the horizon size. And therefore, to fix this, we need to do a third expansion. As you can see, this is how complicated it gets. So we need to perform a third expansion, unfortunately for us, the final expansion, where we instead define Z is equal to small r over capital R, and then do a expansion in capital R, keeping Z fixed. And now you can see that you have a solution that is valid all the way down to the horizon. Eta is proportional to the charge. So we have to do an expansion in eta as well. Eta is also expanded in epsilon and R. And then we fix the coefficients by solving equations of motion at every order. So here's the final picture of what we really need to do to construct these solutions. So we do a perturbative expansion in epsilon and R, and we have to do 3 distinct perturbative expansions. We have to do a far field expansion, a mid field expansion, and a near field expansion. Fortunately, in fact, well, not fortunately, this is the way we set it up, is that there is always a region of overlap between far and mid and near and mid. So you start off by constructing 3 independent set of solutions, but then you can match the 2 solutions by comparing them in their regions of overlap. Well, for small r, it's an infinite size. It doesn't depend on eta. Eta is also expanded in terms of epsilon and R. My parameters for the solution is epsilon and R. So epsilon doesn't show up anyway. So as long as R is really small, which is true because I'm doing a perturbative expansion in R. Eta 0 is going to the soliton limit. Sorry, eta 0 is going to the extremality limit. Yes, that's right. Good. If I go closer and closer to extremality, this is why you can't apply this to supersymmetric black holes. You need more and more regions because as you go closer to extremality, you have an infinite size throat. Yeah. So what happens is, I didn't show it here. When you perform the perturbative expansion, you get terms over here that look like log of R. Log of gamma times R, where gamma is the deviation from extremality. And so you can see that if I'm taking gamma to 0, then the perturbative expansion breaks down when you're exponentially close to the horizon. So you actually cannot construct the solution all the way down to the horizon, which is what we would like to do. So it breaks down exponentially close, which is why this method of constructing the solution cannot be used to construct exactly extremal solutions. Yeah. Okay. Anyway, so the idea is simply this. You construct these three independent solutions. The solution in the far region is fixed. There's some of the integration constants are fixed by ADS boundary conditions. The other ones are fixed by matching to the mid solution. Then the mid solution is similarly fixed by matching to the far solution and the near solution. And then the near solution is fixed by matching to the mid solution and then horizon boundary conditions. Anyway, so it's a whole stuff. You can just do all of them. And here I was just going to give you an example, but in lieu of time, let me skip this. Here are some results. So so here you see the log term that I was showing here, log R that shows up. But when I turn on this is in the static case. So this, if I include a parameter that maps that goes from the static case to the extremal case, this log becomes log of gamma times R. Gamma equal to 1 is the static solution and gamma equal to 0 is the extremal solution. And then you see that if I have a log gamma times R, then in the limit when gamma goes to 0, this term becomes exceptionally large compared to that term. So perturbation theory is no longer valid. So that's when gamma is of the order of e to the minus R, e to the minus e to the R, some exponential function of the radius. Okay, but anyway, so in the static case, at least here are all the explicit solutions. So for the hairy solution, this is the energy. As you can see, it's a 2-parameter solution depending on R and epsilon. You can compute the charges, the chemical potential, the temperature, entropy. All of this can be computed in a perturbative expansion. And this is completely generic. You can do it to whatever order that you want. Here's some graphs showing you how the match of the analytic construction to the numerics. The numerics are the blue dots, and the analytic stuff is the red line. So the chemical potential as a function of energy. You see deviations for large values of energies, which is expected. Entropy as a function of energy also matches really well. And so everything I showed you was with the 2-charge case, but the 1-charge case is exactly identical. We do the perturbative expansion around this point, but the only caveat being that this black dot in the case of the 1-charge case is a singular soliton. So we're sort of doing a perturbative expansion around a singular solution, but we can deal with it because we can hide the singularity behind the horizon. There are extra tricks that need to be taken care of, but it can be done. Okay. What does that mean? Good. I don't know the answer to that question, but I would guess yes.
Yeah.
Yes. Yeah. Yes. Yes. I think that's true. Yeah, we never did it a lot for the soliton, but yeah, that should be probably checked. Good. Okay. So in the last few minutes, let me just now tell you some of the results that we have for rotating solutions. There's not much to report apart from a few plots. Okay. So in this case, what I'm doing, I'm just turning on rotation. So I'm going to show you results for this case where there are 3 equal charges, Q, and 2 equal angular momenta. So this was the case for which George Santos and Julia have already published their numerical results in 2018. The goal here was to simply confirm that the numerics can't really see what happens exponentially close to a black hole, because that's where it breaks, exponentially close to the horizon of a black hole. So we want to confirm that those numerical solutions are actually real, and there's nothing funny is happening as you go really close to the horizon, which is when numerics breaks down. So that's why we would like to construct them analytically as well to confirm this. So here the BPS bound is 3q plus 2 is E is greater than 3q plus 2j. Since all 3 charges are equal, that means all gauge fields are equal, all scalar fields are equals, x1, x2, x3 equal to 1. That means there are no neutral scalar fields. So this is a really simple problem where you just have a single charge scalar field, a single gauge field, and no neutral scalar field. Now, since I have rotation, I need to turn on extra degrees of freedom in the metric as well, which keeps track of the rotation. And here you see that it's still a one-dimensional problem, because one-dimensional in the sense that everything only depends on a single radial coordinate x, but that's only because I'm setting J1 equal to J2. The problem becomes significantly harder if J1 is not equal to J2. Then these things depend not only on x, but also on theta. And you have PDEs. And I don't know if those are actually going to be solvable or not. Okay, and the boundary conditions are exactly the same as before. So in this case, you also have a SUSY limit. So the supersymmetric solutions are they satisfy these additional equations. So any solutions to these set of equations are also they saturate the BPS bound. So one thing we can do, and what we're in the process of working on, is to analyze these solutions and study various near horizon behaviors for supersymmetric solutions. This is ongoing work. Okay, so let me just tell you a few things that we know. Well, numerically, it's already been studied. The analytical construction is exactly the same as what I previously showed you. The only difficulty now being that we have 3 extra functions. So, and with 3 extra differential equations. So it just becomes slightly more. We had 5 functions and 5 differential equations before. We just have 8. For reasons that I briefly touched upon, you can't construct BPS solutions. And the problem is not BPS, the problem really is extremal. And one way I was thinking we can probably get around this is maybe try to construct the Euclidean solutions, because in Euclidean solutions, you can have solutions that are BPS, but not extremal. Then this method will still be usable, because you don't have an infinite size probe, in which case we can find all the BPS solutions there. Okay. And what we're finding is that you construct the solutions, you construct the non-BPS solutions, and then you take the BPS limit. So it's not clear at the moment, and this is exactly why when I say at the moment, I mean to really convince ourselves that the limit is well defined, you have to actually analyze the SUSY equations and confirm that the near horizon behavior that you get by solving the SUSY equations are the same as the ones that you're getting by taking a limit. Then I think then that's a convincing argument that the limit is well defined. But it does seem to suggest that you have a well-defined limit and that you have a supersymmetric black hole. So now let me just show you some plots. So in the 3-charge case, so this is a plot for fixed angular momentum J. So remember earlier, when J was equal to 0, this dot was over here, and the phase space of black holes was of this type, like this. But now when I turn on some angular momentum, you see this part has shifted, and you have black holes. The black holes exist everywhere in this region, and it only touches the SUSY limit at a single point, and that's the Gutowski-Rial black hole. So remember, in this case, where you have all 3 charges equal and 2 angular momenta equal, there's a charge constraint. So it's a 1-parameter black hole solution. So if I fix that 1 parameter by setting J equal to 0.2, then that black hole should be a point on your phase space, and that's this point. So you can see that the extremal limit of all the black holes is not supersymmetric except for this 1 point. But then when you turn on charged scalar fields, you have, again, onset of superradian instability, and then you have new black hole phases over here, exactly as before, and now you have a well-defined supersymmetric limit. And in this case, once angular momentum is turned on in the supersymmetric limit, you do not land on a soliton, which has zero entropy. You actually land on a black hole, which has finite entropy. Good. So the question is, what's happening here? And we don't know. There's a missing phase in this region. We don't know the answer to that. Or if you go back along this line, you go back to Grotowski. But if you ask what's happening on this side, I don't know. The hairy black holes that we have constructed exist in this region. All of these are non-supersymmetric. And now you see you have a whole, well, for a fixed value of one of the parameters, you have a whole one parameter family of supersymmetric black holes. So this calculation has already been done both numerically and analytically. We have also this numerical results for the two charge case. So this is where two of the charges are equal. The picture is exactly identical. That black dot is again the analogous Grotowski black hole in that case. That's the onset of superradiant instability for the charged black holes. And then you have new hairy solutions in this region. And again, in that limit, you get hairy black holes with order n squared entropy. No, because the index, these are the ones for which that quote unquote, that fifth parameter delta is not equal to 0. So anywhere along this line, delta is not equal to 0. But if you take a limit here, delta is equal to 0 here. And the index can only give you delta equal to 0. Yeah. Well, we're trying to understand if we can use some of these complex deformations to extract some non-zero delta, but I don't really see. What I suspect is happening is that these are supersymmetric black holes whose states are those short representations which combine into long. And if that's true, then there's no hope of extracting it from an index. But strictly speaking, when you complexify, we're not really computing an index. We have complexified. There may be some saddle point which can extract these long representations. I don't know. I haven't analyzed it enough. Complexify the chemical potentials. It is determined by the same function, but there's a whole new sets of saddle points in complex. So I don't know if it could be that somehow there's a different saddle point. Well, okay, I agree. I already agree with that. I don't. Yeah.
That's because the entropy formula that
Yeah. Yeah. Well, the way to think about it, another way to think about it is that you can think of f as being the fifth parameter, except that to have an index, you can't turn on a fugacity for f. The fugacity for f has to be e to the I pi in order for everything to cancel. So yeah. Yes. But they won't be, because I don't think they will be, because the delta equal to 0 was coming from that linear relation between the fugacities in the first place. Yeah. Okay. Okay, so that's all I have to say. So let me just summarize. So in previous work, Shiraz, Jyotirmoy, Kyriakos had already studied the three charge case in the static case. In our work in July, we have essentially completed the picture by studying the one charge and the two charge cases. I think putting these three papers together, I think gives us a complete understanding of the full phase space of solutions, of static solutions in this sector of supergravity. So I think that's a complete picture at this point. For rotating black holes, we have constructed two charge solutions have already been constructed. Three charge solutions, well, I should say, since the paper is not out, well, they're under construction. We already have very promising results. And these black holes admit a supersymmetric limit, and they don't satisfy delta equal to 0. So these seems to suggest, give weight to the conjecture that delta is roughly the charge scalar. So I put this in as a point, but I strongly think the answer to this is no. But I wonder if something can be done about this. I'm not sure. But perhaps the more interesting thing is what to do about these 1/8 BPS states, order n squared states that have been discovered on the index side. What we already know is that if you want to explore black holes, it has to be J1 not equal to J2, because the J1 equal to J2 case was already analyzed in the 2006 paper by Raju, Maldacena, and Shiraz. And there they found that if I set J1 equal to J2, then the number of states is order 1. So to actually have a non-trivial black hole solution, you definitely need J1 not equal to J2. But then, of course, the issue then becomes that in that case, the solution is you no longer have ordinary differential equations. They're partial differential equations. They're much harder to solve. But perhaps should be looked into because it's still an open problem. What these number of states, what entropy are these states counting? Okay, so I'm going to end there. Thank you.
I mean, the question of counting the microspace, I mean, the two
Yeah.
we've seen previously, we formulated at least the state that are not perturbably elliptic as a homology problem.
Yes.
At least mathematically well defined.
Yes.
Homology problem really found that it hasn't confirmed that it has a chance of describing local states. So in principle, I mean, that knows more about that. The index is just counting the homology sign, but you can actually
Do the comma. Right.
It's going to be difficult.
Yeah.
But it's well defined out. It doesn't require
I see.
pure theoretic computation. Pure algebra.
I see.
I have a question.
So those we can compute without the sign. So in principle,
Yes.
they might be.
I mean, yeah.
Okay, that's a good point.
I have a question. Can you hear me?
The analogous question is celestial that defines phase of celestial scale. In the state of black holes,
Can't hear
Well, you can obviously simply ask what's the phase space of black hole solutions, which are asymptotically flat. That's a perfectly well-defined question. But it's not clear since we don't know what the dual is. We also don't know which exact theory to study the set, because here I have to study a very precise theory, which because of ADS-CFT, we know has a well-defined dual. So you need to give me which exact theory that you're studying the problem in asymptotically flat. And even if you do that, unless you tell me what it's dual to, I don't know how if we can extract any interesting information from that. Oh yeah, obviously, if you tell me what the bulk theory is and you tell me what it's counting, then this is a good problem to solve. Yeah, yeah.
Okay.
Thank you.
Square.
So just to be sure, in the original real solution, the